So one type of problem you're going to see is an animal pen problem. So an animal pen will be constructed using 90 feet of fencing. The pen will be a rectangle. What are the dimensions of the rectangle with the maximum amount of area? Okay, so what we do know. We know that this is going to be a rectangle. And we know that the area of a rectangle is the base times height. Also, it's mentioning perimeter here, so I'm going to write the perimeter. I've always learned perimeter is 2w plus 2l. So we have a w here, a w here. We also have an l there and an l there. We also know that it's going to be 90 feet of fencing all the way around the perimeter. So we can plug that in. Now this is what we're trying to maximize. And this, we call this the constraint. So I know that I said before that you should always try to write things in terms of of one variable. And now in this case we can't, because width and length could be anything, and I could change w, I could change l separately. But with the constraint here, this constraint is our second equation, so that we can actually then finally someday get w alone. So I'm going to rewrite our area here, and I can write that width times length. Okay, that's what I want to maximize. And my constraint, I'm going to try to get L alone then, so that whenever I have an L, I could plug it in whatever I find over here instead of L for my max equation. So I'm going to subtract 2w from both sides. And then I'm going to divide everything by 2. So this is 45 minus w. Okay, so that means in this equation, I could write w times 45 minus w. So by putting the constraint into the function I want to maximize, I now have an area function that is completely dependent on one variable. And I can actually write it as negative w squared plus 45w by distributing and then switching things around. Okay, and I also know one other thing. This is an upside down parabola. The reason I know that is that the leading coefficient is negative, so I know it's going to be upside down, frowning. And I also know that this point right here at the very maximum, I know that's going to be located at negative b over 2a to the right as the x value, or in this case the w value. So I'm going to use that trick to actually figure out and go right to the maximum. That'd be negative 45 all over 2 times negative 1, which really is just going to be 45 over 2, 22.5. Now the length is the same as 90 minus w, which is just 90 minus 22, or sorry, 40 minus w, which is this just, sorry, not 40, 45, 45 minus w, and that, if I do 45 minus 22.5, the length is also 22.5 feet. So my dimensions are 22.5 by 22.5. Now, if the problem was asking for area, I could just multiply them and find the area. Okay, so there are some variations that you'll encounter. For example, sometimes they're going to put the pen up against a river. Now, the area equation is still going to be the same. It's width times length. But when I look at perimeter is going to change. The constraint equation is going to be 2w and just 1l. So that would change how you work with the perimeter, and you'd have to go back to this, and instead of just you won't have to divide by 2 because there's only 1l. The other thing that could happen is maybe it's backed up against the river and they want to put an additional fence line so that it's sectioned into 2 areas. Well, the length, or the area, is still width times length, but then the perimeter here, or not perimeter, I guess it would be the total fencing we would use, would be 3Ws plus 1L. So with these slight variations, you kind of have to adjust your formulas and your constraints.